Hi friends, in this video, now we are going to discuss its loaded condition on that effect of excitation when prime mover input is constant. Nothing but P is constant, P is nothing but Vi cos pi. This Vi cos pi is constant when V is constant as well as Ia cos pi is constant, because in parallel operation terminal voltage should be constant. Terminal voltage constant, P constant, nothing but Ia cos pi also constant. Right. Now, another P is equals to EV upon XS sine delta. Here, V is constant, XS is constant and P constant. Now, E cos delta or E sine delta is equals to, what is E sine delta is equals to? P XS upon V. This is also constant. Let's draw the vector diagram for this. For example, this is my voltage V, which is constant. Okay, this is constant, is a reference. And for example, this is Ia cos pi. This magnitude is Ia cos pi, which is constant value. Ia cos pi constant value. For example, if my Ia is here, this is unity power factor. For example, if my Ia is here, this is leading load. For example, if my Ia is here, this is lagging load. Is it okay or not? Right, sir. So let's see. This is Ia1, Ia2 and Ia3. In all the cases, the Ia cos pi is constant. Here the power factor angle, this is a phi1 power factor angle and this is phi3 power factor angle. Of course, phi2 power factor angle is 0 because in phase. When this is phi1, and here another important thing, E sine delta is constant. For example, this is my E sine delta. See here, for example, 90 degrees to the current is nothing but our EMF. So see here, what is this? This is Ia1 XS. This value is nothing but our E1. This value is nothing but our E1 and this value is nothing but Ia1 X1. And the angle between this V and E1 is nothing but delta 1. And next one, here this is what Ia2 and 90 degrees to the Ia2 is nothing but, this is Ia2 XS. This Ia2 XS, then this is what? E2. And next one, this is I3. This is I3 and 90 degrees to the I3. See here, like this. See here, this is what? Ia3 XS and this is what? Our E3. E1, E2 and E3, all the values are there. Of course, the angle is delta 1, this angle is delta 2, and this angle is delta 3. E3 and V displaced by delta 3. E2 and V displaced by delta 2, and E1 and V displaced by delta 1. See here the excitation is changes because here this is for leading load, nothing but this is for lagging load, nothing but this is for unity power factor. This is lagging load is nothing but overexcited, and here normal excited, and here underexcited condition for different conditions. This is in generally lagging nothing but overexcited, leading nothing but underexcited. See, what is the observation from this vector diagram? What is the observation? Once, let's draw a graph between, the graph is going to drawn in between excitation, nothing but field current, and the power factor. Excitation and the power factor graph. See, here overexcited condition, the current is this much, and in normal excited condition current is this much, and in underexcited condition again current is this much. Nothing but here this is IA2, this IA2 is less than IA3, and this IA2 is less than IA1. Nothing but see here the power factor. IA cos phi constant. If IA is more, power factor is less. If IA is less, power factor is more. First, to take the normal excitation. For example, this is the field current of normal excitation. Greater than this field current, over excitation. Less than this field current, under excitation. Over excitation, nothing but lagging load. Under excitation, nothing but leading load. Normal excitation, nothing but unity power factor. So, where is the power factor is maximum? Ultimately, at unity power factor, the power factor is maximum. Ultimately, at unity power factor, the power factor is maximum. If the machine goes into overexcited condition, when the machine goes into overexcited condition, is the power factor increases or decreases? It is goes into overexcited nothing but from unity power factor to lagging. From unity power factor to lagging, the power factor ultimately decreases. Because unity to lagging, normal excitation to overexcitation, the power factor decreases. For example, it is goes into underexcitation. From unity power factor to underexcitation, nothing but from normal excitation to underexcitation, from unity power factor to leading, nothing but the power factor again decreases. This is the graph between field current and the power factor. When the excitation is normal, the power factor is unity, and the power factor unity nothing but maximum. When it is going to in lagging, when the power factor from unity to lagging, power factor decreases. Nothing but from normal excitation to over excitation, power factor decreases. From normal excitation to under excitation, power factor decreases again. In both the cases, power factor decreases. When the power factor is maximum, at normal excitation, power factor is maximum. Now, I said you already, Ia cos phi constant. Ia cos phi is constant. We have to maintain. If Ia is first of all, if cos pi is maximum, Then what about IA? If cos pi is maximum, the armature current should be minimum. Now tell me when the armature current is minimum. At unity power factor only, the armature current should be minimum. See here, at unity power factor, this is my armature current. But when goes to lagging increases, when goes to leading also increases. So where the armature current is minimum, at unity power factor armature current is minimum. When it is from normal excitation to overexcitation, normal excitation to overexcitation, armature current increases. From normal excitation to underexcitation, again armature current increases. So see here, when the armature current is minimum at normal excitation, when the power factor is maximum at normal excitation, when it is from normal excitation to overexcitation, power factor decreases, armature current increases. It is from normal excitation to under excitation, still the power factor decreases, armature current decreases. This is called V curve. And this is called inverted V curve. V curves and inverted V curves are observed from this vector diagram only. This is very important. This is under normal condition. If load increases, the curves are increasing like this. Because when load increases, the current increases ultimately. Yes or no? So this is for normally off load, full load, overload, like that. When load increases, curve moves downwards, upwards. So this is the V curves and inverted V curves of our alternator. Is it okay? This is the vector diagram, effect of excitation on our alternator when it is connected to infinite bus bar. Understood? Is it okay? This vector diagram, from this vector diagram, at normal excited condition, power factor is maximum, armature current is minimum. When goes into lagging or over excited condition, armature current increases, power factor decreases. When goes into under excitation or leading power factor decreases, armature current increases. This is generally observed from this vector diagram. Is it okay? Now, they will ask you question. How they will ask you question in competitive exams? Let's see. My alternator operating at 0.6 lagging. If excitation increases, then what happens? It is already operating at 0.6 lagging. If excitation increases, 0.6 lagging nothing but here unity, here 0 power factor lagging. For example, this is power factor 0.6 lagging. When this is 0.6 lagging, again I am increasing my excitation. When excitation increases nothing but, the field current increases nothing but in this way. In this way, what happened to armature current? Yeah, ultimately, when it goes to overexcited, the armature current increases. What happened to power factor? What happened to power factor? See here, when it goes from 0.6 lagging to 0 power factor decreases. What happened to reactive power? Generally, at normal excitation, no delivered. But when it goes into pure lagging, Q delivered increases. What happens, sir? Q delivered increases. What about armature reaction? Yeah, exactly. Armature reaction, demagnetization increases. Because at normal excitation, it is cross magnetization. At over excitation, it is demagnetization. So when alternator operating at 0.6 lagging, if excitation increases, then armature current increases and power factor decreases, Q delivered increases, demagnetization increases. For example, if the same question, if excitation decreases, then what happen? Nothing but this is already at 0.6 lagging, 0.6 lagging. Now the excitation decreases. Excitation decreases, so the armature current also decreases. Power factor is increasing to unity and Q delivered decreases. Yes or no? Q delivered decreases and demagnetization also decreases. Like that they will ask you question. For example, next question. What happened here? What happened here? Alternator operating at 0.6 lagging. If excitation changed to get 0.6 leading. What happens sir here? What they done? Alternator operating at 0.6 lagging. If excitation is changed in order to get 0.6 leading, then what happened to armature current? Now the question. Can you? Exactly. This is operating at 0.6 lagging. Now it is changed to get 0.6 leading. At this condition, the armature current first reduces to minimum, then increases. Armature current first reduced, then increased. Is it okay? What about power factor? What about power factor? First increases to unity, then after decreases. Sir, what happened to reactive power? Can you tell me what happened to reactive power? See here is delivered, here is observed. Here is delivered, here is observed. From delivered to observed, nothing but Q delivered decreases and Q observed increases. Q delivered decreases, Q observed increases. What happened to armature reaction? Here demagnetizing, here magnetizing. Nothing but demagnetization decreases, magnetization increases. This is the way of questioning on parallel operation of alternator with bus bar when excitation changed with the load condition. These questions are very important, sir, and this diagram and this analysis also very important. Or if they want to ask you question simply, the V curves are drawn between. V curves are drawn between. What is that? Field current and armature current. Inverted V curves are drawn between. Inverted V curves are drawn between field current and power factor. Or excitation and power factor. Is it okay? This is clear. The effect of excitation when prime mover input is constant for alternator. So for synchronous motor, now you have to draw. This analysis for synchronous motor, let's draw. Will you draw or not? Okay, draw it first. Hold the video and draw for synchronous motor. Come on. Okay. Did you draw for synchronous motor? Let's see again. Parallel operation of synchronous motor with bus bar at load condition. Effect of excitation when supply input constant here or load constant. Supply input or load anyone. Here P is equals to VI cos pi constant, IA cos pi constant and V constant for parallel operation. And here also V constant, XS constant, so E sin delta constant. So let's draw here the vector diagram for the synchronous motor. See, this is my voltage V. This is my voltage V. And this is IA cos pi. What is this? IA cos pi is a constant value. I said you already. Yes or no? Right? For example, this is the armature current is nothing but unity power factor. This is the armature current is nothing but lagging load. This is the armature current is nothing but leading load. This is unity power factor, lagging load and leading load. Here in synchronous motor, lagging nothing but under excited, leading nothing but over excited, unity power factor nothing but normal excited. Where we can get under excited in magnetization, where we can get over excited in demagnetization, and this is a cross magnetization. Right? Let's. For example, this is now IA1, this is IA1, this is IA2, and this is IA3, and this is the power factor angle phi1. Of course, this is the power factor angle phi3, and of course phi2 is 0. And another important thing is that here the E sin delta should be constant. E sin delta should be constant again. So let's draw. This is, what is this? IA1. So perpendicular to this IA1 is nothing but IA1 XS. This is what our EMF. See, this is what E1. This is the projection actually, like this. And where is E2? This is I2, right? So perpendicular to I2 is nothing but like this. This is IA2 XS, and this is our E2. And where is IA3? IA3 is here. So perpendicular to IA3 is nothing but this is like this. So this is what IA3 XS, and if you draw, this is what E3 and E2 and E1. E sin delta is constant, where this is the delta 3, where this is the delta 2, and this is the delta 1. This is simply the vector diagram for synchronous motor. Even in this condition also, see here, at normal excited condition, the power factor is unity. Nothing but, let's draw the graph here also. This is the excitation, and this is the power factor. This is, for example, normal excitation. If field current increases than normal excitation, it is overexcited. Less than normal excitation, nothing but underexcited. Where we can get the overexcited in leading and in lagging and at unity power factor. What is this leading? Nothing but demagnetizing and cross magnetizing, and lagging here is the magnetization. For synchronous motor, this is not for alternator. Where is the power factor is maximum? As usually at unity power factor, in cross magnetization power factor is maximum. When it excitation increases, nothing but excitation increasing is nothing but leading. See here, this is overexcited condition. So at overexcitation, this is goes into unity power factor to leading. So the power factor, what happens, sir? Decreases. When it goes to underexcited, nothing but lagging, again the power factor decreases. Again the inverted V curves inverted V curve drawn between field current and the power factor only. It is clear. Next, this is normal excited and this is under excited. E1 is under excited. Let's see here. When the armature current is, we have to find armature current. Can you tell me if the power factor is maximum, then the armature current is? Or from the graph, see here the armature current is minimum, here the armature currents are maximum. So when the armature current is minimum, at normal excitation only armature current is minimum. From normal excitation to under excitation, the armature current is increasing. From normal excitation to over excitation, the armature current is increasing. This is called V curves. So V curves and inverted V curves of synchronous motor are also similar to V curves and inverted V curves of alternator, 100% similar. Because both are drawn between IF and IA for V curves, IF and power factor for inverted V curves. This is actually the same thing. Yes or no? Right. Again, once observe this one already, you will get E sin delta is constant, IA cos phi constant, but IA is changing for loads. Normal excitation or unity power factor load, lagging load, leading load, it is changed. Yes or no? Right. Now, how they will ask you question on this? How they will ask you? For example, my synchronous motor operating at 0.8 lagging. If excitation decreases, then what happened? Tell me what happened. At operating at 0.8 lagging, nothing but here. If excitation decreases, nothing but coming to here. What happens, sir? Tell me. The armature current is increasing. Power factor is decreasing. Armature current increasing. Power factor decreasing. What happened to armature reaction? What happened to armature reaction? Magnetization increasing. And Q, nothing but under excited. Nothing but Q observed increasing. Increment in observing. Like that they will ask you question. For example, if the same question, first it is operating at 0.8 lagging. If excitation reduced up to 0, then again excitation increased in reverse direction. What happened, sir? Here 0.8 lagging is there actually. Now excitation reduced to 0. Excitation is reduced to up to 0. Then after again excitation increased in reverse direction, then what happened? Sir, there is no reverse direction, positive direction for excitation because this is a DC. You can give in any way. Whatever, even though if you increased excitation in reverse direction, the excitation increment is same like this. So, what happened here? When excitation reduces, armature current increases. Again, when excitation increases in reverse direction, armature current decreases next. And next armature current increases, power factor increases. And next magnetization decreases. And next Q observed decreases. Very simple. They will ask you question, excitation increased in reverse direction is exactly equivalent to the excitation increased in positive direction. There is no change for both. This is the V curves and inverted V curves of synchronous motor. Are you getting or not? And here you should observe this V curves and inverted V curves. They may ask you question on this. Here synchronous motor is connected to infinite bus bar. Based on that, we given vector diagram and V curves, inverted V curves, which are very important in our synchronous machine. Are you getting or not? Thank you.